Welcome and hello. This is a video exercise using HEC HMS. And in this exercise, we are going to explore the MetSim precipitation and temperature methods. All right, in the description of this video, I've left a link to this webpage right here, so you're welcome to follow along with me. The first thing we need to do is download the initial files for this project. So if you scroll down just a little bit here, you see this download initial project files here link. Just click that and then click the download button. Okay, looks like that finished up. So let's go ahead and close that. Let's see what we have in our zip file we just downloaded. Upper Truckee River. And then here's the data for our HMS project. So I'm just going to go ahead and move that to a location on my computer that I want to save it at. Once that's copied over and unzipped, I can delete the zip file. All right, let's go ahead and open up this project in HMS. And then open, browse. All right, here is my project. And then I'm going to just click on the .hms file and then click select. All right, so the project is loaded up. I'm going to click on the basin model just so I can get a visual of the location. And what we're dealing with here is this Upper Truckee River watershed and the South Lake Tahoe, California age. The model is fairly simple. At least the basin model is just one subbasin and one sink. All right, let's go to the instructions here. I'm going to just kind of follow along on the instructions for this one. We have an introduction to what is this MetSim precipitation and temperature method. So it talks about that, and then it gives an example here where, for instance, if we only have daily data, which is showing up here for precipitation, then this blue line has been created by the MetSim precipitation to represent the sub-daily precipitation values. This method converts a daily precipitation accumulation to sub-daily time steps through the use of a triangle-shaped temporal distribution, and it also depends on the time of year, the time to peak, and the average duration of the storm for that time of year. So we'll see an example of that a little bit later. If I scroll down a little bit more, we have a discussion about how the MetSim temperature method works. So if we only have daily data for the maximum and minimum temperatures, which we're seeing on this plot right here, where minimum for the day is this black line, and then the maximum for the day is the green line. Then the MetSim temperature method will create this blue line here, which basically is the hourly temperature that oscillates between the min and the max every day. Also, this red line right here is the average temperature. If we scroll down a little further, we see the basin that we've loaded up, and we'll get back to that in HMS in just a moment. And then we have the data here. What it talks about is some of the data that we're going to be using in this exercise, which is daily precipitation, the min, max, and average air temperatures, and the daily stream flow. I'm going to go ahead and take a look at those data sets. So I'm going to go up to File, and then Open, and then navigate to the project. And then here in the data directory, I have a lot of data, more than I need. Here is the Livna precipitation.dss. And what I'm seeing in this data set is daily precipitation gridded data sets. So this is January 1915 every day, and then it goes down to December of 2011. So that's a ton of records. What it shows here is 35,429 records. If I highlight just the first few records, I could take a look at the metadata and show that it's not a huge grid, fortunately. If I click on the grid info, I'm seeing that the grid is just 12 cells wide and 16 cells high. It is millimeters of precipitation on a period cumulative data type. There's some other metadata. And then here's back to the grid. Just to make sure that we do have some precipitation, I can click through those grid cells and make sure we have some numbers. All right. So that is the precipitation data set. If I open up the temperature data set, there's a max and a mean for this Livna data source. So let's just open up the max. Let me go ahead and select a record. It looks pretty much what I expected to. That's good. And then checking the grid info. Yep, looks like it's the same data as we had with the precipitation. All right, so I'm going to go ahead and close that. That's the data that we're using. And now we can start with the HMS. So if you scroll down to the instructions here, it tells us to open the project and then start by creating a meteorologic model. So let's go to HMS and do that. We already have our project up and loaded. And then the first step is to create a new MET model for the Livna data. However, we're going to be using the MetSim precipitation and temperature methods. So let's go up to the Components menu, Meteorologic Model Manager, and then click New. I'm going to type in MetSim Livna for the name of that Met model. And then what it tells me to do is to expand the meteorologic model in the Watershed Explorer right here. And now down here in the Components editor, I want to select the precipitation type of being MetSim precipitation, and then the temperature, you guessed it, MetSim temperature. Also, this last field here for replace missing, I want to change that to set to default. Lastly, the evapotranspiration, I also need to change that to gridded Hammond. All right, so up here in the Watershed Explorer, I have a few new icons based on the methods I selected for this Met model. For the precipitation, go ahead and click on this icon here. What we need to do is assign the MetSim Livna data in our components editor down here. So again, with precipitation selected, we're going to select our gridded data set, Livna daily. For the storm characteristic method, we want to change it from fixed value to annual pattern. And then for this storm duration pattern, we want to select our storm duration, which is right here. And then our storm time to peak. This is another paired data set. We want to select storm time to peak. Now, if you want to look at this data, we can as well. This is a paired data set. So we can track that down and find the path and then open up the graph. So here is our paired data. And this is parameter value patterns. And then right here is our two different patterns. So the storm duration right here is, okay, it's just a manual entry. That's interesting. If we look at the table here, now we see the storm duration in minutes, and this is actually monthly data. So using linear interpolation, this is how they did it, where they've got the same value at the very beginning and end of the month for all 12 months, which can be shown here on the graph. The other paired data set is right here. This is the storm time to peak, and they're doing the same thing. It's a manual entry of precipitation type. The time to peak for that storm is shown here in minutes. So we're seeing a value for January and then February and so on. And then here's the graph for that. And then for the temperature, click on that. And we want to select the daily min temperature to be Livna daily min, and then the max temperature to be Livna daily max. Also for this time of daily max temperature, we want to set this to 960 minutes. Lastly, the instructions tell us to click on the gridded Hammond evapotranspiration and use this value right here for our coefficient. So that looks good. We're ready to create a simulation now. So let's go up to the Compute menu, Simulation Run Manager. As you can tell, there's already a few simulations saved here, but we're going to create our own. So click New. We're going to give it this name here, 1972 to 2011 MetSim Livna. Next. This will be our basin model. We're going to use the MetSim Livna Met model that we just created. And then for our control specifications, it'll be 72 to 2011. Right. Now let's go ahead and run that simulation. So let's close the manager. We want to select the simulation run that we just created right here, and then click the compute button. After the simulation, we have a few questions on the screen here. The first one is, what is the approximate storm duration and storm time to peak on December 30th, 2005? How did you find this information? The answer to those questions are already saved in the data we looked at. So let me go ahead and open up HMS. And right down here, the parameter value patterns for within paired data has our storm duration right here. So if I go down to the table data and we saw December, it would be 359 minutes is the answer to that first question. And then the other paired data set here is the storm time to peak. So again, for December, that would be 833 minutes. So let me go ahead and go back and click on the answer. So here it's saying that the storm time to peak and storm duration for that December date was 830 minutes and 360 minutes. Okay, so a little bit off from what I said. All right, let's check out the next question. It is, what is the approximate time of the daily minimum and maximum temperature of December 30th, 2005? How did you find this information? This answer can be found by looking at the results from the simulation and looking at the daily temperature. I'm going to open up HMS and then click on the results tab right here. And then for the simulation run, this is the one and only simulation run we've ran so far. So I'm going to go ahead and click on our subbasin. Now I need to find air temperature, which is right here. Now I have a little preview down here, but this is like 41 years of data, which is a little bit too hard to manage. I can click on this plot icon and zoom in on the plot itself. Click the magnifying glass and then look at December 1995. So I'll zoom in on 95 and I'll zoom in again. We're looking for December 30th. So that's zooming in again. And one final zoom right here looks good. All right, so we're looking at a minimum temperature down here, which is early in the morning, the first half hour of the day. That's 3.79. And then the max temperature is right here. This is what, around 3:30 p.m., and that's 35.6. If I look at the tabulated data, I can see that here. These temperatures are in Fahrenheit. So I'm not going to try to scroll down and find these records because there's thousands of data points. So that's how to get those results right there. I'm gonna go ahead and close that. So you're welcome to go through these questions. If you click here to expand, you can see the answers. Below that in the tutorial, we are going to look at some of the results here for the water years 1972 through 2011. And if you scroll down here, they're using statistics to show how closely the model output results match the observed flows. So in this plot here, what we're seeing is the simulated versus the observed flow at that sink, which is the outlet of the subbasin, where blue is simulated and then black data here is observed. Now, they don't provide any instructions on how to provide a plot like this and how to generate it, so that's what I'm going to do right now. In HMS, I'm going to stay in my results tab here. Let me just go ahead and go to the sink element, and then I'll click on the graph. This gives me the graph for the outflow. What I want to do is click on tabulate, and it's going to give me a table of data for the observed as well as the computed data. Now I'm seeing the computed for the sink and the subbasin outflow. These two columns are the same. I'm going to just click anywhere, Control A to select all the records, and then right click, copy. Now it's going to take a while to copy, so you can see my screen is a little bit frozen. Just give it a moment. Okay, so it finished copying. That took about 30 seconds. Now I'm going to open up an Excel file that I have prepared and then paste that data in. So just paste. What I'm seeing from my results here is a ton of records. Actually, let me just go ahead and scroll down. We have 350,650 records. So like more than a third of a million records here. We don't actually need this last column of data because I mentioned that it was a duplicate. But the first column here is column 5. This is the observed data. And then column 6 is the computed. So I'm just going to go ahead and paste in observed and computed right here. What I have on the screen here on the right, what I've created is a first table here. I'm going to use this table data to create a plot like this. So I need a row for each month of the year, and then the values need to be in CFS. All right, so back to Excel. I have a row for each month of the year. I have the abbreviation, which is used for the formula. And then I have the average value for that month. And this is the flow rate at the outlet. So this equation here that I have highlighted for January observed, for instance, what it's doing is it's going over to this table and it's only going to average the observed flows if there's a JAN string within this date time. For February, I'm doing the same thing, except I'm referencing this February string and searching for the observed values, but only averaging it if there's a FEB substring within this date time, and so on. For computed, it's the same deal, except I'm using column 6 instead of column 5, so observed and computed. And if I just highlight the cell itself here, I'm using the R1C1 formula formatting. So this may look foreign to you if you're used to letters for your columns. But anyway, you can see I'm using the average if formula. The first argument is going to be what I'm looking up and trying to match, which is this column 4 here. That's the date time. And then the second argument here is basically like, you can call it like a regular expression or a pattern that it's trying to match. So the asterisk is kind of like anything, and then January, and then anything. So this RC9 in this case is going to be the month. So I'm anchored on column 9, but not the row. All right, and then the third and final argument is basically the data that it's going to be using to average. So that's how that works. I'll go down to the next row and then highlight it so you can hopefully recreate this Excel worksheet if you want. But anyway, I did that for all 12 months for both observed and computed, got these numbers here, and then I also just created a percent error out of curiosity. What I haven't done yet is created a plot. So we have the data for our plot. What I'm going to do is just kind of scroll over here, grab these two data sets, and then go up to Insert, and then let's see, Line. Okay, let's go Line, and then this one right here, I think is what I want. Okay, that's close enough. Here is a plot. So along the bottom, I have my 12 months of the year, January, February, March, and so on. The blue line here is series one that represents the observed flow rate, and then orange is the computed flow rate. So as you can see, the shape of this plot right here is very much the same as the shape that we saw in the instructions right here. After that, you're welcome to run any other computations or analysis that you want. All right, let's go ahead and scroll down to the next plot. What this is the computed annual maximum flow. So here we have one dot per water year. So instead of having a row for each month, now we're going to have a row for each year. This is going to be the computed annual maximum flow. So this is the model output versus the observed annual maximum flow in CFS. So to do that, I'll go back to Excel. I'm going to scroll back over to the left here. Now I'm going to be using the same data, so I don't have to copy and paste that in again. But if I scroll down a little bit, I see the next table I'm using to get this data, annual maximum flow. And this is a similar equation. It's basically using the year now instead of the month as a substring search within column 4, which is the date time. Instead of searching for JAN for January, I'm searching for 1972, 1973, 1974, and so on. Now I'm using calendar years instead of water years here, just because it was easier, and it's probably the same number anyway. But I left out a 1971 and a 2011 year, so I'm just only using 39 years instead of 41. So here is the resulting observed values and computed values. I will very briefly highlight the equations so you can take a look at it and copy it if you want. Then I'll go down to the next row, then highlight that one as well. All right, so what we want to do is recreate the plot that we're seeing here. So this looks like an XY scatter plot. I'll go back to Excel. I'm going to just scroll over to the right again so I have some space for my plot. I'm going to highlight the data here, observed and computed from the year 1972 down to the year 2010. I'm going to click Insert on my Excel menu, and then for the plot type, down here is the scatter plot, and I'll just select the first one right here. Okay. The last thing I did want to do here is right click and then add a trend line. So let's go with a linear trend line, and then that looks good. I think I can close that. Okay, I also want to add that R squared value format trend line. I think there's okay, display R squared value on chart. Let's see what that looks like. Okay, it's kind of hard to see, but the R squared value here is 0.6949 to represent the goodness of fit for that linear trend line with the actual data on the plot. If I go back to the website, they have a 0.8826, which is a much better fit here. And then this dashed black line represents a one-to-one line. So y equals x, basically. My R squared value is not as strong, but I didn't clean up my data. For instance, the year 1975 and 1979 has no observed data, like no observed max flow. So we have 100% error. And if I just happen to change the computed value to 0 for those 2 years, then the plot updates, and already my R squared value is up to 0.74. So I'm not sure exactly what sort of data manipulation took place to obtain this 0.8826 R squared value, and I'm not going to try to figure it out. But anyway, I was just going to show you how to capture the data and then also how to create this plot in Excel, as well as the first one we did. All right, so let's go ahead and scroll down on the instructions. There's a third plot right here you're welcome to try out. That's the annual exceedance probability, and I believe that's the last plot we have here. Yes. Okay, next on the instructions, we're told to create another simulation, and this is for 1915 all the way to the year 2011. The instructions are shown here. Create a simulation, and then make these selections when you create the simulation for the basin model, met model, and control specification. By all means, go ahead and do that. It's a similar process to what we just did, and you can obviously compute the results, copy the results to Excel, and create some pretty cool plots. I'm not going to do that. It takes about 10 minutes to run the simulation, but I will just stop right there and just say that in this exercise, we used the MetSim temperature model and precipitation model to come up with graphs like this for use in our HMS model to compare the observed flow with the computed flow from the model, which can be used for future analysis.